In this presentation, we're going to be looking into plotting the data for Kepler's third law in Mathematica / Wolfram Cloud. Basically, Kepler's third law relates the planet's period to one of its axes, basically the distance the planet is from the sun. And it is a scaling law or a power law. We start by entering the data. The data will be a set of data points, x, y combinations. The x will be a distance from the sun, and the y will be a period in some unit that we will show later. Previously, when we entered the data, we named it Kepler, so we are going now to make a list plot of the data Kepler. We are going to add a title to that plot, so we use PlotLabel arrow. Remember, to make the arrow, you type a minus sign followed by a greater sign, which is then turned into the arrow. We're going to keep the title simple, so it just quotes Kepler's third law, end quote. And we are also going to have axis labels. So the third argument is AxesLabel arrow, same thing, a dash or a minus sign followed by a greater than symbol turns into the arrow. The axis labels, there's an X and a Y, so it is a set, so the curly brackets. We're using here HoldForm. The distance is going to be in 10 to the 11th meters and the period in 10 to the 7th seconds. And the HoldForm does some formatting for us. So HoldForm square bracket distance, the word distance, and then in parentheses 10 caret 11m, close parenthesis, close square bracket. But you can see when you see the x-axis label that 10, that the 11 is treated, you don't see the caret at all, and the 11 is treated as a subscript. That was the effect of HoldForm. So again, ListPlot, the first argument is Kepler, which was the data. The second argument here was PlotLabel with the little arrow, and that is the main title. We kept that simple. Then the axis labels, there was an X and a Y, an X-axis label, a Y-axis label, so the curly brackets. We had some formatting to do in terms of using the power as a superscript, so we used HoldForm. And so then we had to close the curly bracket of the XY pair, then finally close the square bracket of the list plot, and you see the result. Next, we would like to fit this data to a power law. So we're going to use the FindFit method. So we have in in3 Kepler fit. That is just a name that we've given to the fit. So Kepler fit equal, we're using the FindFit method, capital F find, capital F fit, square brackets. Then the first argument of the FindFit method is Kepler, which was our data. The second argument is the form that we would like to fit to. So we are saying A star x raised to the n. We announce next as the third argument that A and n are fitting parameters. So we are going to find the best A and the best n. And then x, the last argument, is saying that that is the variable. So A times x raised to the n, where A is a fitting parameter, n is a fitting parameter, and x is the variable. Shift enter, and then it gives us the best fit A and the best fit n. A is the coefficient out front, n is the power. Let's point here that we've switched to FindFit, whereas previously we were using linear model fit, but our parameter here, the n parameter, the power parameter, is not linear. So linear would mean that it was simply sort of multiplying something out front. And remember that the linear and linear model fit is referring to the parameters. So we could have something like a polynomial and it would still be a linear model fit. But because our parameter in this case is a power, that parameter is not linear, and therefore we're using the FindFit approach. Now we could turn the problem into a linear model fit. And that's what Excel does for a power law, and that's what we forced R to do. We can take the logarithm, the log of our x's and our y's, and then our fitting function becomes linear in the power. The power then becomes a linear parameter, and so one can take that approach. But Mathematica has a way to handle it by keeping n as a power. Here we are taking the two parameters we found, the coefficient, the a, and the power, n, and we are plotting that function, and we're plotting it over about the same range of data that we saw in our Kepler data, so x going from about 0 to 60. So just plot square bracket the number a times x raised to the n, those numbers we got from FindFit, comma, and then curly brackets, and the variable is x, and we're going from about 0 to 60, close square bracket, shift enter, and that makes a plot. And we want next to combine this plot with our ListPlot of the data. So here we are using show. We are combining the ListPlot, which was out2, with the plot of the fit function, which was out5, and we're adding a display of the equation, and that is that Epilog inset. Okay, so again, out2 was the ListPlot of the data that included the main title and the x and y axis labels. Out5 was the mathematical function that we found from FindFit, which had a power close to 1.5 and some coefficient out front. And so that is the dots were from out2. The line sort of connecting the dots is from out5, and the axis labels and the title were from out2. And we are also adding a displayed equation, so that is the epilog. We have the arrow. Remember, you make the arrow by the minus sign followed by the greater than sign, which turns into the arrow. And then we are going to inset. So then inside the inset, we have a HoldForm. Remember, HoldForm does some formatting. So in particular here, it's going to take the caret and not show the caret, but take what's after the caret and raise it up as a superscript. So inside inset, inside HoldForm, we have y equals 1.737, x caret 1.498. And so that is the displayed equation. And then after the HoldForm, we have a comma, and then we have curly brackets 2600. This is an x, y, which will be the position of the inset. So we see that if we go over to about 20 on the horizontal axis and then up about 600 vertically, we see that that's sort of the middle of the position of the displayed equation.